works. It'll take a few seconds.
It's warm.
Is it too warm in here?
I opened the window a few minutes ago.
You can just
Okay. Hello, everyone. I'm Sam. This is my area exam. One thing before I start is to make sure people are paying attention. I have 1 bar of chocolate. I've hidden 1 mistake. Not a grammatical mistake, but like a logical mistake. So misplaced comma. I've hidden 1, so if you find it, you get a chocolate bar from France. Okay. Let's see. I'm going to start a timer.
I just want to say I would get it, but I'm on a diet. So
Okay. Well, all right.
Okay,
And if
I will match with an apple.
yeah.
okay. Well, we'll see if you find it. All right. I wish I had a clicker, but this is how we are. Okay, so I'm kind of going to start. So my title is called Verification Techniques of Low-Level Programs. I'm going to spend a lot of time talking about verification techniques and low-level programs. I'll sort of explain what that is, but that's sort of an application, right? Because I'm going to basically give you an introduction to formal methods and tell you sort of more about just the building blocks of these, because they're used throughout all sorts of verification techniques. And then sort of the low-level programs I'm focusing on is like floating point arithmetic, sort of SIMD parallelism or vectorization, and then intermediate representations. So the question was, why do I pick these 3 topics? So you're going to see sections 3, 4, 5. I'm sort of interested in low-level, right? And what I mean by that is not very much abstraction, right? So at the most abstracted math, we might have category theory, distributed systems, where the unit of abstraction is you're dealing with a whole computer, whereas with vectorization, you're dealing with a single register or a set of registers. Likewise, with programming languages, we have assembly, right? So this is the level I'm comfortable working at, is low level. So that's sort of a little motivation. Okay, so what is formal methods? In 5 seconds, I would say it's using math to make sure your computer does what it's supposed to do. I think that's a good, someone asked, and I'll bore them if I talk anymore, right? So for some stranger, I think that's a good introduction. But slightly more formally, it's the application of theoretical computer science, math, type theory, logic, and even some philosophy applied to computer programs, to the analysis of computer programs. So I kind of think of it as like a coin with 2 sides. The first side is the specification, and the second side is checking that the program obeys the specification. And these are so central. These are like the 2 aspects of formal methods, right? So the first one is when you design a machine-readable specification. Formal is something that's machine checkable, right? English is never formal, no matter how formal it sounds. Something might be like a logical formula, program in a language like Coke, and maybe even the type of a function could sort of be considered a specification, right? And so the next step is ensuring the program obeys the specification, and you do that with a blank checker, type checker, what have you. So then in math, this parallel is you write a theorem and then you prove the theorem. And this actually is a very deep connection. There's a very deep connection between this. It's called the Curry-Howard correspondence. It's a very famous result sort of in theoretical computer science, that proofs and programs are very deeply connected. So the question would be, next is, why do we need formal methods? It's very classic bugs in computer science have resulted in deaths or millions of dollars in damages. So one example would be a radiation therapy, which gave people 100 times the dosage because there was a bug in the software. Another example would be a Patriot missile had a timing error, which ended up killing 28 people. So then these are some very serious cases where computer software can have bad consequences. So then I'm going to start to talk about sort of paradoxes and how we came about to reasoning about computer programs in this way. And this is a very old sort of paradox that humanity has been grappling with, right? The classical, this statement is false, is how do you make a computer explode? The issue here is with self-reference, right? You're referring to yourself. And the analog in Lambda calculus is that is Curry's paradox. right? So this is sort of, you can create this non-terminating function from which you can prove anything. And this is not something we want to do because, you know, we prove something impossible, right? So to get around this, Alonzo Church invented the simply typed lambda calculus, and this, so formal methods in some sense predates computers. So this was around in 1940, and so one other aspect of the simply typed lambda calculus is it's total. So all programs terminate. What that also means is it's not Turing complete. So there's some things we cannot compute. For example, maybe an operating system kernel, which you don't ever want to terminate. And so here's one quick example, right? There are many ways to express the same thing in lambda calculus. You might want to say this is a Boolean instead of the first function of a pair, accessing of a pair. All right, so now I'll give like a very brief introduction to logic. I can't do this in one slide, but I'll just sort of refresh. We have propositional logic, which is if and only if and or implies not. And then, you know, that's applied to various different other formula. And so what we might ask about logical or propositional logic is, can we satisfy this collection? Can you guys read that? Fine? Okay. I wish that, anyway. So can we determine the satisfiability of a given formula? And this is a famous, I think this is the first example of an NP-complete problem. You can check it quickly, but you cannot, as far as we know, determine if it's satisfiable quickly. So sort of the thing with logics is the more expressive you get, the less well you can reason about it, right? So we have, if we were to explain the rules of chess using first order logic, that requires 1 page of like written explanations, but propositional logic requires 100,000. So this is one example. And then if we use, so then first order logic is something with existential and universal quantifiers, so things that apply to the whole, you know, everything in the universe, right? For all numbers, something happens, right? So this is just very brief introduction to logic. So, you know, a lot of formal methods will work on propositional logic or first order logic or even higher order logic. And in those cases, like first order logic and higher order logic, you cannot in general decide satisfiability of some statement. But that doesn't mean we're out of luck here. There's some. I'm going to talk briefly about some canonical verification techniques that people use, and these have been around for I don't know, 40, 50 years, and they're what sort of the building blocks, like I was mentioning. Yeah. I think there's no more chairs. You have to get a couple chairs.
We are selling tickets, by the way.
Oh. Yeah. Or you could watch it on YouTube. Yeah, get some chairs. You couldn't get it? Oh, shoot. Not that one. Huh. Waiting for me? Okay. It says it's streaming. Okay. Well, if that, you know, this is more important. I'm not going to debug that. Okay, so I'll start to talk about verification techniques, Hoare logic, satisfiability, modulo theories, and abstract interpretation. So Hoare logic, you might have seen this before in an algorithms class where you sort of provide a precondition and a postcondition. You describe sort of what a statement is doing, and then you see at the end what you get out, right? So we might have something like x is greater than 5, and we multiply x by 2, and then we have x greater than 10. Now, this is not strictly the strongest condition, right? If we're dealing with integers, we know that x is, in fact, greater than 11. But, right, so then this brings up the question of how do we compute what is, in some sense, the tightest bound on our application, or on our program, right? So this is that Hoare logic and all the semantics for that, for a given programming language. Satisfiability modulo theory. So this is the satisfiability we have, right? We have these Boolean state or form variables, and we add some theory of whatever, right? That might be integers, floating point, lists, you know, data structures computer scientists use. Now, I say this is like the matrix multiplication of formal methods, right? In the sense that it's sort of a very, you know, at the core of a lot of algorithms, right? This is sort of the back end, and it ends up being where most of the compute time is spent, right? You might develop some sort of something at a higher level reasoning, and then you spit out some SMT satisfiability. formula, and you number crunch on that. So we have some example, right? Satisfiability of integers. We can put in x and y. I think it's 6 and 8 for those, and get satisfiability. So that's what an SMT solver will do, is figure out these sort of inequalities, right? So I won't dwell on that too much. So okay, don't ignore the thing. Actually, that didn't turn out
The
at all.
error is not in there, right?
No.
No.
This is kind of a
Alright.
yeah. So this is I wish you could see it, but you don't need to pay attention to it. It's kind of funny because it's a sort of infamous. The inventors of abstract interpretation are sort of known for being not easy to follow. So they wrote this little 2-page paper that is this dense, completely jam-packed with formula. So it's kind of fun to look at that.
Basic.
But it's it's basic Galois connection. You know, the abstract interpretation is you can really clearly define it as well as sound static analysis. So sound means there's no false negatives. If it says there's no error, there truly is no error. There might be false positives, but there are no false negatives. Static analysis means you discover properties of this program without having without executing it, right? So these are the abstract interpretation. I'm going to go through an example because I think this is valuable, and also I'll start to talk about the floating point sort of complexities, which is going to be a big part of my future work. So suppose we have a function, and all we want to do is 1 divided by some number, right? So I call this unsafe function, and you know, as we all know, you cannot divide by 0. So now we just check, right? So what we want to do is verify that this never misbehaves in some sense. It will always return something finite. So the way we do this with abstract interpretation is we have to first create an abstract domain, which is a set that is not that's not all the floats, right? It sort of simplifies it, and I'll show you that in the next slide. And then you define semantics on that abstract domain. So what does it mean to divide with these values? And then you interpret, so you run your program and you see what you get, right? So this is all done without actually executing for some value, specific value of x. And this is sort of a general trend with formal methods, is you look at your program and then you don't see variables as just plain variables, right? You don't put a 5 in for x. You see it as something more symbolic or more abstract. Okay, so continuing with this example, here's our abstract domain, right? So we have the, we have some non-zero. So I'm making five different values. I have a 0, a non-zero, a nan, an infinity, plus or minus infinity, or just some float. If we don't know what the floating point value is, we just have to assume it's float. But importantly, float is either any one of these 4, right? So then what we have is we have 1, which is a non-zero. We have some non-zero divided by the first column. And what do we get? We get, and then the equals, the second column is what we get out, right? So I checked these because I couldn't remember how all these worked, but we have some non-zero divided by 0, we get infinity. And that's handled. But all these other 3 cases are not. And I put float here. I didn't mark that because that's sort of, the float is broken up into these 4 cases, right? All right, so then we need to modify this to get like something better, right? So I guess in some sense what abstract interpretation told us was that this is not good enough, right? We found we can't prove anything about the output of this function unsafe. So now I redid it. I said mostly safe. So now we check for infinity and not a number. Only problem though is, right, this shows one of the issues with floating point numbers. There's not always an inverse for a number. So we have the not a number and the infinity case handled, but then even if we get some number, we have 1 divided by a very, very small number, we end up getting infinity as an overflow. So, this is some sense like incomplete, right? We still can't reason about this. So just to keep everyone happy and I did it correctly. This works for every single floating point number. I know because I tested it. And so it's kind of nasty, right? These are saying you have sufficiently small numbers. And maybe there's a better way to do this, but the bits are easier to check exhaustively. So in some sense, we have abstract interpretation kind of falls flat. One way to fix this abstract domain would be, instead of having some non-zero, we would split between really small numbers and not really small numbers. right? And one way we could say that a floating point number is say whether it's subnormal or not, but that's sort of beyond the scope of this. But anyway, here's sort of an example of how abstract interpretation works, right? You make an abstract domain, and you operate on that. You define the semantics for that abstract domain. Okay, so next what we'll talk about a little bit is formal methods in practice, right? How do people actually use this stuff? How do people actually verify properties? And so this is a little bit my knowledge from my work this last summer at San Diego National Labs. They do formal methods in practice. And I wish they were online. They could get a shout out. But okay, so sort of there's 3 design decisions, and of course I don't know how someone designs, but this is how I see it. So what degree of confidence do we want to have? What do we want to do to accomplish this, right? Do we want to just prove that maybe we don't get any null pointer dereferences, or do we want to prove something stronger, like this software shall never crash, or on any input it will behave nicely and not, give 100 times radiation to someone? So how do we accomplish that? And then how much, there's this trade-off between human and computer time, right? And it tends to be the more automated methods prove weaker properties, and I'll show sort of an overview of this. So formal methods is sort of, it's not a silver bullet, right? You can't solve everything with it, as you saw with abstract interpretation. I say it's more like a flu vaccine. I know this is maybe a little bit controversial in Oregon. Flu vaccines are good, but they are. So here's an example here. There's a security vulnerability that was found in the WPA2. It's a Wi-Fi security protocol. And that protocol had previously been proven secure. So you wonder, how did that happen? Well, it turns out that this was a vulnerability related to temporal property, right? And the WPA2 standard didn't specify this. So this goes back to my explanation of formal methods is only good as its the thing you prove is only as good as its specification. And so there's a famous Donald Knuth quote, right? Beware bugs in the above code. I've only proved it correct, not tried it. So, there's not everything we can do, but I will describe, how we can get increasing levels of assurance, right? Because ultimately this is sort of a human endeavor, right? It all relates to how we interpret things. So we have on the right, and I'll be using this example throughout, and so the details, not too big of a deal. It's just trying to compute, trying to figure out if Fermat's last theorem is false. So we have and recall Fermat's last theorem is for any n greater than 2, a to the n plus b to the n equals c to the n has no integer solutions. So we're checking this, right? We're checking, and this is just for a cubed. So a cubed plus b cubed equals c cubed is false for all integers. This is known. The question was maybe some basic safety guarantees we might want to ask are, will IPAL work for all integers? And in this case, it will not, right? Because if we put in a negative number into x, it'll just recurse until stack overflow, probably. So these are sort of things that can be handled mostly automatically with like an SMT solver or some static analyzer. So we can find out bugs like that, or we can maybe find if array, in a lot of cases, if there was array down here in this double nested for loop, if these array bounds are ever broken, right? These are the sort of properties. So not anything about correctness, just saying this program will behave better than, the average program you write, right? So the next question you might ask is, well, does this test all combinations, right? Are we skipping something? Are we skipping the case where a equals b or something like that? So typically in order to do this, we'll need a loop invariance or annotating code, right? With this Hoare logic, perhaps you have a precondition and a postcondition. You check the code ensures this. So now once we have that, we can prove partial correctness. And what does partial correctness mean? Well, it means if the code terminates, then we have a right answer. Now this is different. This code will never terminate. Suppose that the integer was a larger, arbitrarily large integers. Then we know this code will not terminate because Fermat's last theorem has been proven. But anyway, we have partial correctness, which is in a lot of cases good enough. So then the next question is, does this code terminate? And that turns out to be a really, really hard problem. This was one of the most famous, if not the most famous, unsolved problems in math for about 275 years, until Andrew Wiles proved it in 1985. So again, like these sort of things, these questions we ask about computer programs can range from kind of trivial to stumping all of humanity for 275 years. So we have a big space to work with. And I like this tweet. You can see well, you can't see on this, but I retweeted it. So this is sort of talking about the tools formal methods people use, and we have a very different in the community a different check for whether something is good, right? So you know, a software engineer, you really care about linear, right? Maybe when designing an OS. Complexity theorist is either polynomial time or non-polynomial time. Verification researcher, almost everything we do is exponential or worse. So then if it's decidable, it's great, right? Most of the things, like I mentioned, first order logic satisfiability is in general undecidable. That being said, a lot of these work surprisingly well in practice. We oftentimes end up actually being able to compute properties or having a satisfiability theory, which, as we know, is non-polynomial or exponential time. These will scale a lot higher, a lot further than we want, or than we would expect if the runtime truly was exponential. It's just exponential in the worst case, right? So this gives us hope that even though if something is undecidable in general, a lot of the times it will terminate. So this is sort of one of the key figures for my presentation, right? We have this trade-off we want to have, right, between automation and the strength of the properties we generate or we prove. So what prevents us from reaching this sort of holy grail is we have a fundamental limit of computation, right? So this is never going to exist. We're never going to get a completely automated thing that can prove anything we want about a program. It's just impossible, right? This is known as Rice's theorem, but it's sort of a fundamental limit about computation is that a Turing machine cannot reason about anything non-trivial about itself, right? A Turing machine might be able to say, well, I have this one state, but it can't really say, well, I know I'm going to halt or anything like that, right? So we can't get to here. It's impossible. That's why it's the Holy Grail. It doesn't exist. But we have all these different. I'll talk about each of these in turn, but we'll talk about each of these that can sort of. We have this trade-off, right? All right. So at the bottom we see proof assistance, bottom right. So these are almost not automated at all. But you can prove anything you can prove in math. I think that's true. Anything you can prove in math, you can prove with a proof assistant, because essentially it's just also doing math. So the famous ones, and there's a list here, but Coq is the sort of the primary, most mature project. It's out of France, and I have these two checklists here, and one is the De Bruijn criterion, and one is supporting tactics. So the De Bruijn criterion is essentially saying, well, suppose you have someone who's really, really skeptical about every programmer's skill, who writes Coq or HOL or whatever all these are, and he will say, well, I don't trust this computer program unless I can manually verify it, right? Because you have essentially what proof assistants do is they generate this proof and then they check it. Right, and this is the specification versus verification duality I mentioned earlier. So then the De Bruijn criterion says, well, I need to be able to verify the verifier, this needs to be simple. So languages like Coq, what they end up doing is they have a very small kernel language, and they compile everything you might write into this kernel language, and they can check that. And this is a few hundred lines of some code, and it's been widely tested, right? So even the most skeptical person might say, well, it is a computer, we cannot trust the computer. And you say, well, it's simple, you can verify it, you can look at it by hand. And you say, well, I cannot trust the compiler. And you say, well, this compiler has been used for various different things. You say, well, I cannot trust the hardware. And then you say, well, I run this hardware or you run the program on many different pieces of hardware, right? So there's always going to be some level of lack of assurance. But at the same time, I would argue that this is a much greater assurance than someone handwriting a proof, right? There have been examples, not a whole lot, but of proofs that have been accepted and then found incorrect later. So this is about as high of a standard, I think, as we can get, the De Bruijn criterion of a proof assistant, to really know that something is true. But the trade-off is we don't have much automation, right? And tactics are one way to provide a limited form of automation for proof assistants. And a tactic is a program which finds a proof. So a program might try, it's like, what are the tactics used to try and make this theorem true? Right, you might try and swapping x and y if we know x and y are commutative, or the addition is commutative, or something like that. And these don't generalize super well. You kind of have to do this for each problem domain. For example, reasoning about analysis, real analysis, has very little to do with the correctness of a compiler. And these are both things that have been proven in code. So you have to sort of write these things on your own. Now there's a list of these, and I don't know, they're various ones. There's not a whole lot of them. This is a relatively complete list, but each, Intel has their own, and University of Texas and AMD, they're both in Texas. They probably do some stuff. I'll mention HOL and ACL too, because hardware community has really taken advantage of formal methods, whereas software has not as much. And I think the reason why is because bugs in hardware are a lot worse, in the sense that you can't just go in and download a patch to a hardware. You have to do a recall. So Intel had a famous bug in, I think, the early 90s with floating point arithmetic, which was, there was a mistake. Just, I don't know how bad it was, but they recalled all their processors. And they say it's a $500 million mistake. I kind of think that they just had the balance sheet say it was a $500 million loss so that they could recoup that, right? Get the books better. But regardless, that's what they told everyone, is a $500 million mistake for a bug in the floating point. I think it was a divider or something. So anyway, hardware manufacturers very much know the value of formal methods. So when costs of bugs are high, this effort is worth it. Okay, I saw the movie. The Martian, and I'll take the press when I can get it. This is some PVS code. This is a proof assistant. So it's completely it doesn't make any sense here, because this is supposed to be a video transmission file, and for one, it's in plain text, and for two, it's in a programming language. So this doesn't make any sense, but whatever. It's still there. It's actual code from NASA's repo, and you go on their GitHub, and they're very happy. They say, "Look, this is on the Martian and such." So this is kind of fun. If only it was more realistic. Okay, so now that I've given you all sort of an overview of formal methods, I'm going to start to talk about some some applications. So these are the things that I'll probably be working on, but I've sort of given an overview, right? So intermediate representations or intermediate languages are an attractive application for formal methods, because you sort of get a lot for free if you can verify things about an intermediate representation. For example, in LLVM, we have a bunch of programming languages which compile down to it. Right? And also they're sort of, in some sense, closer to hardware, right? So this is the area I'm comfortable with. We have WebAssembly, which actually has some machine checkable semantics, and this WebAssembly is meant to be checkable. WebAssembly is new. It's meant to be assembly for running on web browsers, so that you can get this high performance code on a web browser, which seems sort of like it wouldn't make sense, but this is the goal, because we have increasing dependence on apps for webs. So Vellum is LLVM in Coke, so that's verified, and it's another project. Binary Analysis Platform is another project. I won't really get into those, but they are they're what I base my work on. Okay, so the next part I'll spend a little more time on is floating point arithmetic. So there's this tension between interpreting a float as a real number and a float as just a collection of bits, because it plays this dual role. And so we have the way to represent floating point numbers is with IEEE floats, and they have these quirks, right? For example, you have the same bit pattern that's neither necessary nor sufficient for these two numbers to be equal. So if we have not a number, which is a floating point number, as I mentioned in my earlier example, they can have the same bit pattern, but they're not equal. Meanwhile, there are two ways to represent 0, which are equal, but the bits don't look the same, right? So if you interpret these floats as bits, you're going to check equality, you'll get the wrong thing. Right, so these are really challenging problems because people who do real analysis or numerical analysis tend to treat these floating point numbers as approximation to the real numbers, and this is not a valid approximation. But if you treat them as bits, you don't get anything we know, because real numbers have these nice properties like x plus y is equal to y plus x, and these obvious things about real numbers that we know how to reason about. So there's this tension, and I think I'm going to go back and talk about. I have an example in the SMT solver, and I'm gonna bring it up again because it was kind of flashed by it, but not there. Okay, but this is sort of an example, right? And it looks kind of complicated, but it's not really saying that much. All it's saying is if you have here, this bottom here, x is less than or equal to y, and you add some small z to them, right? It's not suddenly the case that y is less than x. You don't just swap. If you have 3 is less than 4, you don't suddenly have 4 is greater than 5, right? That's all that's saying. It's not too crazy, but if you try to run an SMT solver on this, on the floating point, it does what's called bit blasting, and it says, well, let me try every bit combination of every single floating point number. And this just doesn't converge, right? I ran this for a few hours on, albeit it was on this MacBook, but I ran it for a few hours and it didn't converge. And this is only 1, 2, 3, 4, 5 different statements, right? So this is a problem with floating point arithmetic. Something like this with integers can happen very quickly. The integers are sort of more nicely behaved because we know how to add them and all this stuff. They behave closer to bits. But floating point numbers are a different beast. They're much more complicated because what we're doing is we're trying to represent a finite and uncountable set in a finite number of bits. So there's an issue here. Okay, so what are the attempts to formalize real numbers? We have a Coq library called Flock, and this doesn't concern itself with bit-level representations. It has a way to encode it, but it's just saying a floating point consists of these things. The other thing is there's no maximum exponent. So this overflow problem that I mentioned in my example about abstract interpretation, that would not be caught by Flock because this is sort of, they say, well, this is a separate issue. So you'd have to use other machinery to check these overflow conditions. So there, Flock is lacking. It's still a great project, I think, because they have a lot of different theorems that they've proven, and if I were to expand on this, I could use them, but it's still not complete. Okay, so the next step, next section I'll talk about is SIMD parallelism or vectorization, and I'm attracted to this because I've noticed in the past a trend of vectors getting more and more used in computing, right? So GPUs, they're not strictly vectorized, but they do a little more than that. But if you can express something as vector operations, right, doing always the same operation on a big chunk of data, using derivative parallel primitives or however you want to do this, you get incredible speed up. So this is sort of the trend I'm noticing is that vectorization is getting more and more important. So the question would be, why is this challenging? And we have this increasing vector widths means, for one, these instruction sets are getting bigger and bigger. The more vector widths, the more you have to account for 2 vectors with 2 vector with 4 with 8th, and then all of the conversions between them and all of the permutations of them, and it gets just very, very complex. The Intel, I had the numbers somewhere, but I think the Intel manual for this is 2,500 pages or something, and they kind of stop telling you at a certain point because it's their proprietary stuff. So this gets horribly complicated. It means you get a more complex control flow graph, and this is also, it becomes difficult to automatically vectorize. Because there's so many different options, and also difficult to hand vectorize. Ultimately, we end up being forced to hand vectorize because the computational scientist might know some property, like, as I mentioned, x plus y equals y plus x, or you can distribute multiplication or factor it. So then these sort of properties of real numbers, and generally, you can use vectorization for not real arithmetic or floating point arithmetic, but this is sort of going to be my focus. The other thing is these are also done they're very hardware dependent, so we're done at this intermediate representation level, right? So then the study of intermediate representations, ILs, IRs, will help for this. But these code transformations, oftentimes, if you do something like GCC OFAST or O3, they'll assume things that aren't true, right? So for example, floating point arithmetic is in general not associative. And if we recall, associativity is, well, anyway, I should have written it down. This doesn't sound good if I say it. But anyway, so these are too aggressive because associativity does not in general hold. The code transformations.
Okay.
Just press it down.
Thank you.
Code transformation, again, so that's too aggressive. Too conservative is when, and this is existing research I've looked at, they assume code transformations must match exactly scalar code. Now, this isn't always true, right? Sometimes you can do a little bit of commutativity. Or even if it's incorrect, we might want to know what error bound, right? So if we're running some scientific computation and we only ever, we stop once convergence hits 10 to the minus 6, but now we're worried about here 10 to the minus 15. This is just noise that we don't want to care about with this. We can afford some loss of accuracy, or maybe we can't, right? So then knowing under what cases we can afford this loss of accuracy and not afford this loss of accuracy is just not known. There's not work. I mean, there is work on this, but it's definitely an unsolved problem. Okay, so now I'll sort of conclude. I went a little bit fast, as I do when I'm presenting in front of people, but I'll sort of I have a few extra slides. Okay, so if we recall, formal methods is two things. It's the sides of the same coin. It's creating unambiguous, computer checkable specifications. And then it's model checking, right? It's making sure these specifications, the program obeys this specification. Now, theoretically, many of these formal methods algorithms are NP-hard or worse, right? They're maybe even undecidable. But in practice, these scale surprisingly well. So, right, for some sort of exponential program, we would not expect this to scale beyond n of 35. And what does n of 35 mean in a computer program? That would mean 35 lines, right? Or 35 branches, right? And no interesting, that's not true. Most interesting programs are longer than 35 lines. So we can, end up scaling in the hundreds or thousands, but eventually, we get these Google's code base or something, million-line programs. This is not incredibly scalable for these complex algorithms. So there are methods that I didn't get into that will reduce this complexity. One example would be if we have some loop that is going to loop all the time, we will bound the number of iterations. We say, well, this is only going to loop 1,000 times, and then we can sort of reason about this a little better. Okay, I might as well. Okay, I'll explain these pictures. So I'll go way back to the beginning, since I have the time. So the two sides of the same coin. I picked this coin on purpose because this is from a Jose Luis Borges story called The Zahir. And the story goes, this man finds this coin, and he can't stop thinking about it, and it's called a Zahir because he cannot stop thinking about this coin, and that's all, and then he goes insane. So formal methods is my Zahir because that's all I'm going to be thinking about for the next 2 years. And then back to here. This is a little more hopeful. This is the Aleph is another story by Jose Luis Borges. And it's about a guy that thinks about everything, right? Instead of thinking about just the coin, he can see everything in the universe. So I think it also makes him insane. But, right? But the reason I like Borges' stories is his stories all deal with handling infinity, right? How humans can't really grasp the infinity. His most famous story is the Library of Babel, which is about an infinite array of, it's not infinite, it's a finite but very large library that has every single combination of every single letter in this collection of books, right? So how do we reason about this, right? And I think this is relevant because the state space, oftentimes with formal methods, is so unreasonably huge, right? We get a million-line program and we're dealing with 2 to the million of a state space, which is so unfathomably large. The number of atoms in the universe is about 2 to the 150. So this is that, you know, it's completely ridiculous to explore all of this, right? As with the Library of Babel. But we make do, right? We wander around in the dark until we figure stuff out. So one complaint about formal methods is it's too expensive in the sense that it takes too much time, too much programmer time. And I think this is not really a valid complaint. In some sense, yeah, you don't need, you write a web app, you don't need to prove everything is correct. But it's not all or nothing, right? And I didn't really go into this all the way, but we have these static analyzers that are more automated. We have abstract interpretation, which can be somewhat automated. Even think of a type checker, right? If we're programming in a statically, strongly typed language, we can get these actually quite nice properties that you don't get. I personally, I've done a lot of bash programming, and I've done a lot of Haskell programming. So this is sort of the two opposite ends of the spectrum, and I've shot myself in the foot in bash a lot because I don't have types. I can't reason this. I say adding a string to a number, and it just does that, right? It'll just concatenate, and that's not what you want typically. But anyway, so formal methods is not all or nothing. We have type checkers, which have been widely used. We have static analyzers that can oftentimes be used as a continuous integration for software engineering, the workflow. So we have something like Microsoft. I believe that all their driver code, whenever a developer pushes, it runs a static analyzer. This is running on 24/7 to ensure that anything you write, anything a Microsoft developer writes, will not also break every part of Windows. And this is why, I don't want to advertise for Microsoft too much, but this is why you can sort of just theoretically plug in any hardware into your Windows machine and it will work. Because they do, part of the reasons why they do all these static analysis, which is formal methods. Microsoft Research is a really big contributor in the formal methods community. We have Microsoft Research in France. Those are the two places where I read maybe half of my papers. So again, another thing would be like red squiggly lines in Eclipse. If you're programming something and it goes, I don't like this. This might be incorrect, right? This is, in some sense, formal methods. It's doing some static analysis to ensure that you have, maybe it says, oh, this variable is uninitialized. It's not technically incorrect, but it's probably not what you want. And I have another example of another formal method. You say, well, it's too expensive. Well, there was this rocket, this European rocket that blew up. It incorrectly converted a 64-bit floating point number to a 16-bit integer. So that was expensive because I think it set back their whole program, cost them $500 million because rockets are expensive, right? So this floating point thing is, and this was, I believe it was in the early 90s. But it's not solved, and they're challenging problems. But I think it's worth the time to make sure your code is right. Let me see. I think another slide. Oh, I have to put an XKCD comic because it's computer science. So this is the one about voting machines. I couldn't fit it all, but you got the text. So basically, if you tell someone that they trust a voting machine, we laugh, right? And this is sort of a different philosophy that we have with respect to computer programs than we do. With normal programs, or with anything else. For example, you have a bridge you build, a civil engineer builds a bridge, and you expect the Brooklyn Bridge to stay up for a couple hundred more years. But imagine saying, well, here, I'll start this web server, and then we'll come back in 100 years and see if it's still working, right? This is just completely ridiculous. But we're not there yet, because it's like a different philosophy, because for one, software is a lot easier to swap in and out. But I think that also it's a younger field or something. I don't want to posit why companies make these billion-dollar decisions, but this is sort of a different philosophy of computing versus real-world engineering. All right, so I kind of talked about my future work a little bit. But I'll bring it up a little more. So we have we have all these different floating point formats, and I want to unify how these can be represented, right? We have some ones before IEEE floats, we have IEEE floats, and then we have new ones like one called posit, and that claims a lot, but there's not been a lot of work done because it says 2 years old. People don't really know how well it performs or how correct it is. And then I want to unify like this idea of floats as bits versus floats as real numbers. I want to look at SIMD transformations, like I mentioned, that they're either too rigid or too aggressive or too conservative. And then another project I have called Chameleon. I made this. You can have O'Reilly books online, so I made like a fake O'Reilly book about it. This is actually kind of cool because this has people working on it. It was a summer project for me at Sandia, and then now I can't claim it anymore because like I should. Well, I think my first name. I think my name's on here somewhere, but it's oh, okay. But yeah, it's not mine anymore. There's 4 people working on it, which is kind of cool. Like my summer project continued, but I would like to continue using this Chameleon tool, which basically what this does is take multiple different assembly language, maybe an IR or maybe even just straight up binary, and then does some analysis on it, right? So then this could be used. I think this is what I'm going to end up contributing to a lot in the next couple of years. Yeah. Okay. So those are my that was my area exam. I wish I had gotten the stream to work, but I don't know. I tested it and oh well. So nobody else gets to see it. You guys are the only 15 or 20 of you. I don't know how many there are. So yeah. Thanks for. Are there any questions first?
Let's thank you.
Oh, okay.
Where was the error?
There was no error. I was just to get everybody to pay attention. I
Oh.
fooled you guys. Fail. So I'm giving this chocolate.
I've never checked Boolean formulas so carefully.
Exactly.
Now everyone pay attention.
That's not fair.
There'll be a chocolate bar for every person in the room.
There was
Whoever
a
came the
grammatical
furthest gets it.
Grammatical error count?
No, grammatical errors don't count. I said in the beginning. Well, everybody paid attention. So that was it.
Okay. Questions from the audience?
So I had a question. You brought us back to the SMT solver slide to explain something, and I wasn't really sure.
Oh, you want me to go back to that?
Yeah.
It's.
Because that,
No, I know what you mean. It's a very simple thing, but it can't be expressed nicely, unfortunately, as far as I know. So, okay.
Yeah, like the last thing down there that x is less than y, and you add 2 to it, and y is less than that.
All right. So my claim is this is impossible. This is not a true thing. There are no values for x, y, and z that this is true. Right. So we're saying if we have 2 numbers, for example, 1 is less than 3, and we add some small z to both of them, right? We have this inequality 1 is less than 3. That's true. We don't suddenly get the inequality 2 is greater than 4.
Okay.
Right. So it's like we don't get a flip flop, and this is I wish, and I tried to think of a better way to represent this, but that's how you would symbolically. Does that make sense? Okay. Are there any other questions? I kind of went, as I always do, I kind of went too fast through the first 3 quarters of it, but I don't know.
Are you still going to give out the chocolate?
Yeah, to whoever came the
To
first.
the one that asked a question.
Oh, to the one that asked the question. Oh, that sounds more fair. Yeah.
Aw.
Few
Okay.
questions, yes.
I don't have any more chocolate, sorry. You guys probably feel duped.
We done with questions anymore?
Your stream's running right now, by the way.
Oh, it is?
Yes.
On YouTube?
Yeah, the whole thing.
Oh, good. Okay, that's great. I'm glad to hear that.
I don't know about audio,
Well, hey, thank you. No, the mic was turning on and off, so okay, that makes you feel a lot better because now it's saved. Because it doesn't say, it just sends it off to the internet, and it's YouTube that decides to save the information. So it doesn't save it on my local computer.
So were these India people online trying to participate online?
Yeah, maybe I could take I said I would take questions from them.
but someone was commenting.
Okay.
Oh, was Jeff there?
The volume seems really low. Well, I didn't know how to boost it. Okay, so now I'm going to be... No. Gotta mute that. Okay, so it's not showing the chat. Oh, okay. Oh, there we go. We got it. Okay, it took some time. I'm really happy this worked out. I was worried that it wouldn't. Okay. Oh, that's not a question. Thank you, Philip. Maybe there. Oh, okay. Okay. Oh, wow. Okay. We got a troll. Oh, great. Happy to notice you omitted the Book of Sands. This bodes well for the continuance of your obsessing over formal methods. I have not read the Book of Sands, but I will add that to my read list. I'll put it here. I really like Borges, but he only writes short stories, so it's can be hard to track down all of them. Okay. Anyway, so I didn't know people would actually watch. That's great. It looks like I have. Oh, never mind. 0, 0. I was going to say, it'd be funny if I had 1 like and 1 dislike. Okay, I think I'm going to end the stream. Thank you for everyone for tuning in offline.